Hans. So I wanted to just make a little video walking through my Python code for this. I felt like that would be the best for all three of us. It helps me practice this, and then I am not sure how familiar you are with the methods I'm about to explain, but at the top I have a little instruction manual with some links for what I've done, what resources I've used. What I'm aiming to do is go through the proteomics data that I have so far. You can ignore the data cleaning for the most part. Mainly, I just want to talk about false discovery rate and that I did Wilcoxon Signed-Rank tests for baseline to immediately post-training, which I'm calling Rec2, baseline to Rec21, which is the very last day of training, the very last testing visit. And then for all three time points, I did a Kruskal-Wallis test, which is a nonparametric equivalent of a 1/3 ANOVA. So the first thing I have here is the data set that I have. This is all of the proteomics data. You can see that there are missing values throughout this. And so the first several chunks of code are just me cleaning it up, getting it to how I want it, where there's no missing data in certain data points. You do have this attached so you can follow along. I'm going to try to make this quick, hopefully that you can pause or go back to the documentation that I've attached as well if you have any questions. So what I'm getting to here is I took the raw abundance values and I did a log2 fold change for all of the values that I'm going to be doing analyses on. This is from baseline, so baseline value should be 0, which you can see down here. And then this is to that immediately post-training time point, so you can see the respective fold change from baseline. The same thing will be done for Rec21. So first thing I did is I plotted the highest 50 log2 fold changes from baseline to Rec2. And then if you want to grab those values, this is a list of those values graphed. And then similarly, I did the lowest 50 log2 fold changes. And again, you have those lists. This protein calls, this is how I filtered the data, but these are all of the proteins that are in both baseline and Rec2 time points. If you wanted to just grab all 209 of those, I believe. Briefly, this is the Wilcoxon Signed-Rank test for baseline to Rec2 time point. What I have to do is, because there are so many different data points being tested, there's a large percent chance of a false positive. And so that's what the false discovery rate methods for correcting the p-values do. Specifically, this is the Benjamini-Hochberg equation or correction method. This link is pretty helpful. I've attached this. This is from a genetics group at UNC Chapel Hill. This is also just a longer overview if you wanted to read it. I think this is an excellent video. This method has been cited over 100,000 times, so it is a very commonly used method. So briefly, just running through the code, I've corrected the p-values, and I do not have any significant proteins identified for fold change from baseline at the Rec2 time point. The next setup, I'm just going to skip through this because it's the same thing, but it's baseline to Rec21. Again, you have the top 50 proteins, a list of those proteins. You have the lowest fold change proteins and that list of proteins. Here's my Wilcoxon data from baseline to Rec21. Again, I have made the corrected p-values here, and there are no significant proteins identified for fold change from baseline at the Rec21 time point. There's a little summary for that right there. The third thing I did was the 1/3 nonparametric ANOVA, so the Kruskal-Wallis. Same setup. These are slightly different data sets, so I did plot them because there are just slightly different amounts of proteins that are identified in all sample time points. Same thing, negative or lowest fold change at these two time points in the that are abundant in all three data sets. And then lastly, Here's the Kruskal-Wallis data set for statistical analysis. And once again, I got the p-values, adjusted them using Benjamini-Hochberg, and then here are my corrected p-values. I sorted this just to kind of see the lowest, and 0.2 for this protein was the lowest corrected p-value that I have. So at this time, with these three methods, this was the initial plan of attack that I had that I discussed with David via email a couple months ago. There are no significant proteins identified, so I just wanted to reach out and try to get the ball moving and see if there are any other suggestions to try. This was my first swing at this. Thanks.